This is fundamental problem 2 from chapter 13. If the motor M exerts a force of 10 t squared plus 100 newtons on the cable when t is in seconds, determine the velocity of the 25 kilogram crate when t is equal to 4 seconds. The coefficients of static and kinetic friction between the crate and the plane are 0.3 for static and 0.25 for kinetic, and the crate is initially at rest. So we're going to start off drawing a free body diagram for this problem. We have the force of gravity acting downwards, we have the normal force acting upwards, and we have a force of friction acting in the opposite direction of the motion, or of the motion that there would be if there was no friction. And then we have what they call the force that the motor exerts on the crate. Whoops. That's supposed to be the normal force. So the motor exerts a force on the rope exerts the force on the crate. So if we want to call it tension, we could do that, but I called it F there, so you can make that a T. Or you could call it F sub M for the force that the motor exerts on the crate. Every force that we have acting on an object should either come from something that's touching the object, or it should be a non-contact force. The only two non-contact forces that we have that will be relevant for this course are the force of gravity and the electric force. And usually we don't have to worry about the electric force. So we have the force of gravity acting on the object, and then everything else comes from something that's touching the object. The rope is touching the object, so we have the force of tension, and the ground is touching the crate, and that exerts a force in a direction which is perpendicular to the surface, which is the normal force, and also a force which is parallel to the surface, which is the force of friction. Okay, the crate does not move in the vertical direction, so let's say this is the y direction, that's the x direction, so the acceleration in the y direction is equal to 0. We can sum up the forces in the y direction using Newton's second law, and we have let's just say the upward forces are equal to the downward forces since the acceleration is equal to 0. So the sum of the forces in the y direction is equal to 0, therefore the normal force is equal to m times g, and that's 25 kilograms times 9.81 meters per second squared, and that gives us 245 newtons. They gave me the coefficient of static friction and the coefficient of kinetic friction. I only need static friction if the crate isn't moving to begin with, but before the crate moves, it has to overcome the static frictional force. And, let's see here. When time is equal to 0, the tension is equal to 100. So let's figure out what the maximum value for the force of static friction is, which is what we get when we use the coefficient of static friction times the normal force, which is 245. And that is 73.5 newtons. So, does the crate move immediately? When time is equal to 0, the tension in the rope is 100. So you have a force of 100 newtons pointing this way, and the maximum value that you can have for the force of static friction is 73.5. So if you can only have a force of 73.5 pointing this way, then the crate is going to begin moving immediately. So the crate begins to move immediately, and now we can look at the force of kinetic friction, which is 0.25. So notice that the coefficient of kinetic friction is smaller than the coefficient of static friction, which is almost always the case. And we have for the coefficient of for the force of kinetic friction, 61.25 newtons. Okay, so now we can look at the sum of the forces in the x direction. The crate is moving in the x direction. I don't know what the acceleration is. I have tension pointing in the positive x direction, so that is 10 times t squared plus 100. And then I have the force of friction pointing in the opposite direction because the crate begins to move right away. We have the force of kinetic friction right from the beginning, pointing in the opposite direction, so we have the negative sign there. And this is equal to the mass of the crate, which is 25, times the acceleration in the x direction. We're trying to find the velocity when t is equal to 4 seconds. Well, I can use what I have here to find the acceleration as a function of time. So I'm not looking for the acceleration, I'm not looking for the time, so I might as well simplify this by dividing by 25 to get the acceleration, which I can then use with my kinematics equation, hopefully, to find the velocity. So 100 minus 61.25 is 38.75, so I have 10 times t squared plus 38.75 divided by 25, and that gives me 0.4 t squared plus 1.53. So now I have the acceleration as a function of time, and I am looking for the velocity. I know the acceleration is equal to dv dt, and if I have the acceleration in the x direction, this would be the acceleration in the x direction is equal to the derivative of the velocity in the x direction with respect to time. I can rearrange this and say dv dx is equal to ax dt. This is the acceleration as a function of time, so I can put that right in here. I'm going to integrate, and when time is equal to 0, the velocity is equal to 0. And then for my upper limits of integration, because I'm looking for the velocity when t is equal to 4 seconds, I can either put in for my upper limits of integration just t and let's say vx, or I could go ahead and put in the 4 and now, and then I can find the velocity when t is equal to 4 seconds. So when I integrate on the left-hand side, I'm just integrating dvx. So I just get dx when I plug in the limits of integration. And then we're going from 0 to t. We have 0.4 t squared plus 1.53. So when we integrate on the right-hand side, we have 0.4 times t cubed divided by 3 plus 1.53t. Plugging in the limits of integration just gives us the same thing back again. So then if I want the velocity when t is equal to 4 seconds, I have 0.4 divided by 3 times 4 cubed plus 1.53 times 4, and that gives me 14.7, and this is meters per second. That's the x component of the velocity, but the crate is not moving at all in the y direction, so you could also just say that is the speed of the crate. And what did they ask us to find? The velocity of the 25 kilogram crate. We could write it like this. The velocity is 14.7 meters per second in the i-hat direction because we have defined our coordinate system there. And that concludes fundamental problem 2.